In standard microeconomic analysis, we typically study extremes, the absolute control of an isolated monopoly, or the atomized lack of control in perfect competition. But most real industries operate in the messy middle, where a few dominant players command the market. This is an oligopoly. Look at the Ghanaian economy. Sectors like telecommunications and the banking industry, regulated here by the Bank of Ghana, are textbook oligopolies. In these markets, a firm cannot optimize in a vacuum. Its best move depends entirely on anticipating the specific reactions of its rivals. Because of this strategic interdependence, standard price-taking models fail. Economists require an entirely different framework to predict how these firms will behave and what prices consumers will ultimately pay. That framework is game theory.
This grid represents a normal form game built on 3 precise ingredients: a set of players, the strategies available to them, and the payoff functions that determine their profits based on everyone's choices. We can apply this to a classic prisoner's dilemma. Here, Firm A and Firm B must simultaneously choose whether to set a high price or a low price. If Firm B prices high, Firm A maximizes profit by pricing low to steal the market. If B prices low, A must also price low to survive. For both players, undercutting is the dominant strategy, locking them into a $10 profit when cooperation would have yielded $20. This trap is a Nash equilibrium. It is a state of mutual best responses where no single firm can improve its profit by changing its strategy unilaterally. By calculating the Nash equilibrium, we can mathematically predict the exact pricing and output decisions of competing firms, even when they are strictly forbidden from communicating with one another. Our first major application of this is the Carnot model. In a Carnot duopoly, 2 firms compete by simultaneously choosing their production quantities, and the total market volume determines the final price. This equation is the Carnot profit function. When a firm attempts to maximize this function, it must treat its rival's output as a fixed, unchangeable constant. Taking the partial derivative with respect to the firm's own output and setting it to 0 isolates the best response function. This formula tells a firm exactly how much to produce given any theoretical output from its competitor. We can plot these algebraic best responses on a 2-dimensional graph. Because both firms are performing the same calculation simultaneously, we get 2 downward-sloping reaction curves. The exact coordinate where these 2 reaction curves cross is the Carnot-Nash equilibrium. At this specific point, each firm's output is the mathematically perfect response to the others. Applying the parameters from Self-Check 2.1, where market demand is 100 minus 2Q and marginal cost is 10, we solve the equations simultaneously. Each firm produces exactly 15 units, resulting in a market price of 40. The negative slope in these calculations proves that quantities in the Carnot model act as strategic substitutes. If your rival produces more, your profit-maximizing response is always to produce less. This equation demonstrates the N-firm Carnot equilibrium, showing what happens when the number of firms in the market increases. By converting this into the Carnot learner index, we see a direct inversely proportional relationship. As n rises, the industry markup shrinks perfectly in tandem with the fraction 1 over n. But consider how the math reacts if we change the rules of engagement. What if firms compete by setting prices rather than choosing quantities? This animation illustrates the Bertrand paradox. Because consumers will completely abandon the more expensive firm, 2 price-setting competitors will endlessly undercut each other until the market price crashes down to exact marginal cost, erasing all economic profit. In practice, this total destruction of profit is rare. Real-world capacity constraints prevent one firm from absorbing the entire market, and product differentiation gives consumers reasons to buy that aren't strictly based on price. The critical insight is how sensitive market predictions are to the strategic variable. Swapping quantity for price completely rewrites the mathematical outcome of the competition.
We must also account for markets where decisions are not simultaneous. In the Stackelberg model, a dominant market leader commits to its decision first, forcing a follower to immediately react. This timeline illustrates how the leader calculates its move using backward induction. The leader precisely calculates the follower's future best response and embeds that reaction backward into its own present-day demand curve. We see this in action in the derivation for Self-Check 6.1. By substituting the follower's reaction into its own demand, the leader sets marginal revenue equal to marginal cost and optimizes its output at exactly 40 units. The leader then pushes that output into the market. The follower has no choice but to optimize against that massive remaining demand, yielding a best response of only 20 units. Compare this to the simultaneous Carnot model, where these identical firms would produce just under 27 units each. The math proves the existence of a first-mover advantage. By acting sequentially, the leader commands a larger share of the profit, pushes total industry output higher, and reduces the overall deadweight loss for consumers. While these models show firms competing, the participants would earn significantly more if they colluded, restricting total output to the monopoly level and splitting the inflated profits between them. Yet the very structure of the market fights against this. Following the prisoner's dilemma logic, every firm in a cartel has a strict, immediate mathematical incentive to secretly increase production and cheat its partners. To prevent this, collusion requires an infinitely repeated game. Firms use trigger strategies, the guarantee of severe future retaliation, to enforce cooperation today. This balancing scale illustrates the stability condition. The quick cash grab of cheating must weigh less than the infinite stream of future cooperative profits, multiplied by the discount factor, delta.
Because delta measures patience, collusion requires firms to heavily value future payouts. Without high patience and perfect observation, cartels naturally collapse under the weight of their own economic incentives. These theoretical models are not purely academic. Regulators and competition commissions rely on them to detect anti-competitive behavior in actual economic data. This formula is the Herfindahl-Hirschman Index, or HHI. It is the primary tool used to measure market concentration. By squaring the market share of each firm, the index heavily flags industries dominated by a few large players. We can bridge the gap between this real-world data and our theoretical models. The math dictates that the Carnot-Lerner index equals the HHI divided by the market's elasticity of demand. Econometricians exploit this relationship through conduct parameter estimation. The input observable market data, like prices, overall quantities, and demand elasticity, to solve for a hidden behavioral variable. Once isolated, this single conduct parameter provides the empirical proof. It tells regulators exactly whether the firms are competing fiercely, behaving as a standard Carnot oligopoly, or illegally colluding. The structural math of game theory provides the exact blueprints necessary to enforce antitrust law, break up monopolies, and protect consumer welfare. This summary matrix ranks the expected outcomes of the 4 oligopoly models based on total output, price, and overall industry profit. Looking specifically at the price column, the hierarchy is strict. Collusion extracts the highest prices, followed by Carnot, then Stackelberg, and finally the aggressive price matching of Bertrand at the bottom. When solving these models, avoid the most common calculation traps. For Stackelberg problems, never try to solve the equation simultaneously. You must use backward induction. Second, when calculating the Herfindahl-Hirschman index, always use whole numbers for market percentages, never decimals. A 50% share is 50 squared, not 0.5 squared. Mastering these algebraic derivations is the essential prerequisite to analyzing market power. Ensure you can perform these calculations step by step before moving on to the live problem-solving sessions.